we should define a relation on Z by X related to Y if and only if X squared is equivalent or logically equivalent to Y squared mod N, mod 4, right now. Then they say we must check if this is an equivalence relation. First, we need to know what is an equivalence relation, right? We need to know what is an equivalence relation. Remember, when we talk about an equivalence relation, first, we're going to say that R is called an equivalence relation. Let me just do this relation. If it is reflexive, reflexive, symmetric, and transitive. You see, right? That's when we can call something an equivalence relation. Now, we're given this question. We're given, they say that X is related to Y if and only if X squared is congruent to Y squared mod 4. Right? In this case, what we need to know is that this is logically equivalent to X squared, or is the same thing as X squared minus Y squared, which is equal to 4K for some K element of an integer. You say, right? You need to know that this is equivalent to that. So now we need to come and prove what we call reflexive. Then we prove what we call symmetric. Then we prove what we call transitive. So for the first thing you do, if you want to prove reflexive, right? First thing you do, I want you to come and write reflexive so the lecturer knows what you're dealing with. So when we are proving reflexive, we'll be starting here. Right? We won't start here, but we'll be starting with what we were given. Now, for us to prove reflexive, guys, don't start here. I want us to come first and let an element or some object. For reflexive, we need to let one element to be an element of that set which were defined on, which is Z. So we're going to let X be an element of Z. Then, or we can just say for any X element of Z. You say, right? I'm sure you can agree with me here. I can even say for any. You can say that for any X element of Z. So if we take X from Z, I'm going to replace this one by X. I'm going to have X squared congruent to X squared mod 4. You say, right? Now, if we continue to prove this means that X squared minus X squared, using that definition, X squared minus X squared is equal to 4K. You must also include this for some K element of an integer. Right? Which this will imply that this is 0, which is equal to 4K. Then this implies that 0 is equal to K. And this is indeed true because we said for some K element of an integer. So we were saying that it's possible that maybe one value can satisfy the condition, and we found that value. You say, right? We say, now since we have this, we're going to come and say, thus X is related to X if we find that this condition holds. Now we say, so R is reflexive. I'm sure we say this. Now we come to symmetric. When we come to symmetric, the aim for symmetric, remember symmetric is in the form of if, then. If this, then this. And here we're saying that if x is related to y, then y is related to x, meaning we must assume this. You see, right? So we're going to come and say, first we need to say for any xy element of this. Or in most cases, when we come to this one, we will dive deep into the concept of the predicates. We're going to say it would be best for us to say they exist, or for some. Or let's say this, let's use this signs. I think if we use the signs, it will be fine. We can say they exist xy element of an integer. So every time we come to symmetric and transitive, instead of saying for any, we're going to say they exist. Because it's possible that it might not be all, but it might be some, right? They exist xy element of z. Then we say x will be related to y, we're assuming the hypothesis. And this they said if and only if. Remember to use the signs which are given there, right? If and only if. They said if and only if x squared is congruent to y squared mod 4. And the aim is to find that y squared is congruent to x squared mod 4. This is what we want to find. So we're going to solve and see if we're going to find it. So let's do that. So remember I said that after applying the definition here, you know that this means this, right? For k, for some k element of an integer, right? We know that after applying this definition, we need to commute for symmetric. For us to prove that something is symmetric, we're going to commute these two. Then we factor out the negative after commuting. Then this will be y squared minus x squared, which is equals to 4. Then the negative will be taken by the k. You see, right? Now we have this. Now we say that 4 minus k element of an integer. You see, right? Now we have this, and we know that this means that y squared is congruent to x squared mod 4. This is what this means. You see, right? And if we arrive here, automatically we know that y is related to x. Automatically it means that y is related to x. So we know that we have proven this, that if x is related to y, then y will be related to x. So this is how we're going to prove for this question, right? So we're going to come and say thus R is symmetric. I'm sure you see this. Now we come to transitive. We come to transitive. When we come to some transitive, we're going to say that there will exist some 3 elements x, y, z, element of z. Then this one we prove that if x is related to y and y is related to z, then x will be related to z. You see, right? This is what we're trying to prove. So we'll assume this. So we're going to assume that x is related to y if and only if. This one we know that it's when x squared is congruent to y squared mod 4. Then we say and we assume the other part, which is y squared. Let me say y related to z first. If and only if y squared is congruent to z squared mod 4. I'm sure we say this. Now, from here, we can expand the two concepts. If we check, we can come and say that x squared congruent to y squared mod 4 implies that x squared minus y squared is equals to 4k for some k element of an integer, and we know that y squared congruent to z squared mod 4 implies that y squared minus z squared is equals to 4p. I will use the same constant, right? For some p element of an integer, right? Now from here, we can add this side and also this side. We see what we get. When we add them, we are going to say, then we add them, we say x squared minus y squared plus y squared minus z squared is equals to 4k plus 4p, which this implies that x squared minus z squared is equals to 4k plus p. And this we can say for k plus p element of an integer, since k and p are an element of an integer. Now this implies that, you remember that this is the same thing as saying, x squared congruent z squared mod 4. You see, right? Indeed, we have proven this. We arrived to show that x is related to z. Then we say, so x is related to z, thus R is transitive. Now, since we have proven that R is reflexive, symmetric, and transitive, and now it means that we can deduce and say that R is an equivalence relation. So we're going to come and say, for our conclusion, we're going to say that since R is reflexive, symmetric, and transitive, it means that R is an equivalence relation. So this is our conclusion. Any question here before we jump to the next question? Any question? So if no question, it means that we can jump. Let's see. Then also another one said that we should look at, let me say this. I'm just gonna tick the one which we just did now. So now we look at this one. Let's say look at G. We have 5 to the n minus 4n minus 1 is divisible by 16 for all n element of a natural number. So I'm just gonna take these questions going up, right? Now, let's see. We are told to use, the question says we should use PMI to prove. You say right now? So we're going to use the principle of mathematical induction to prove this. Now, for us to prove this, what we should do, we are going to first do this. Let me write solution. the right solution. We're going to first let Pn such that 5 to the n minus 4n minus 1 is divisible by 16 for all n element of a natural number. Don't forget to include this part, right? Now, I include this. Now, from here, we check, we have three things which we need to check here. We need to check the base case, P of the first number, which is covered here, which is 1 in this case. Natural numbers start from 1. Then we check P of k. Then we check P of k plus 1. This one, we're going to check if it's true. This one, we're going to assume that is true. Then this one, we are going to deduce that it is also true. Then prove using this one. So this one are going to work together. You see, right? So it means that what we are going to be checking first, we check P of 1 such that when I check P of 1, it means that I'm going to plug here 5 to the 1 minus 4 1 minus 1. Then the question is, what do we get here? The thing we get 5 minus 5 is 0. Then since we get 0, we're going to say which is divisible by 16. Hence, so 0 is indeed divisible by 16 right now. Hence, P of 1 is true. So that was our aim. We were supposed to check if P of 1 is true. Next thing, we're going to assume. For P of k, we're going to assume P of k is true. For some, this is very important, you must specify that for some k element of a natural number. You say right, so you're just replacing n by k. Now, after this is called the inductive hypothesis. You say right now. Now, we're going to come and say, if we assume this, we're going to come and say, we have 5 to the k minus 4k minus 1, which is equal to, in this case, they say that this is divisible by 16, which is similar to saying this is a multiple of 16, right? So we're going to say this is equal to 16. We can't use k anymore. We have to use some variable, 16p, for some p element of an integer. In this case, this should be an integer. Now, we are going to do this. From here, we are going to make one thing subject to the formula, right? We can make 5 to the k. As always, when you're working with these ones of divisibility, you're always going to make one thing subject to the formula from the assumption. You say, right? So we can say that this implies that 5 to the k is also 16p plus 4k plus 1. We just keep it like this. Then we come to the deduction part, pk plus 1, such that, and then we deduce p of k plus 1. We're going to say p of k plus 1. Deduce p of k plus 1 is also true. Then we just say, we're not going to specify this, right? We've already specified it in the previous assumption. So we're going to say now 5 to the k plus 1. So come and replace k by k plus 1 minus 4 k plus 1 minus 1, which is equal to 16r for some r element of an integer. We use a different variable here. So now let's check this. We have realized that we did make 5 to the k subject the formula here. So it means that here we need to make sure that we get 5 to the k. So we can drop one thing here. You see, right? So it means that we're going to say this implies, or not just imply, let's just take the left hand side first, then we'll imply later. So the left hand side is equals to 5 to the k plus 1 minus 4. Let's simplify this. Minus 4 minus 1. This is equals to 5 to the k, 5 minus 4k minus 5. Now we must prove that this is equals to this, right? And we know that 5 to the k is 16p. 16p plus 4k plus 1, right? Now we see this, that this is 5 to the k, and then we multiply it by that 5, minus 4k minus 5. This is equals to, what is 16 times 5? Guys, what is 16 times 5? Let me just use a calculator. It's 80p plus 20k plus 5 minus 4k minus 5. So I know that the 5 will cancel out, right? Now this will be left with 60p plus 20k minus 4k. Then 20k minus 4k will give us 16. So let's also simplify that. So I'm glad you can see now how are we getting 16k. Now we factor out 16 because we're looking to show that this is 16r, right? When we factor out 16, we know that 80 times 5 gave us 16. So it means that here we'll be left with 5p plus k. Then we replace this by r. We know for r equals to 5p plus k, which this is an element of an integer. And indeed we found that this is equals to 16, which we have proven the right hand side. Then we're going to deduce here and say thus p of k plus 1 is also true. Then we say hence p of n is true. Our condition there was for all n element of a natural number. So this conclusion is very important, right? So you should keep this conclusion in mind. So yeah, so let's look at this. Let me see what other question that you guys were asking. Yeah, now let's come to algebraic structures, right? There was also a question based on algebraic structures, but we can start with the one of a Boolean algebra. We can start with the one of Boolean algebra. So let's say we're given this. Let's say they say let b 0, or then they give us 1, they give us and they give us a negation. They say let this be a Boolean algebra. Let this be a Boolean algebra, and they say xy is an element of b. Then they say prove that, or prove the following. They say prove the following. Then they give us this a. They say we must prove that 0, negation of 0 is equal to 1. They say we should prove that the negation of 0 is equal to 1. You see, right? So now we're given this. They say the question is, or let me check, I think once did something like this. Let me check. if we didn't, unless if it was contact, right? Let me check if it's not here. I think, yeah, I think it might be that it was contact. It might be that it was contact. Yeah, I think it was contact, but it's fine. Let's let's prove it. So now we are given that the negation of 0 is equal to 1. So there are many ways to prove this, guys. There are many ways to prove this. What we need to know is that we need to know the logic laws. You see, right? You need to know all the logic laws for you to be able to prove this. So now let's go back to the logic laws. If we go back to the logic laws, we have these laws that we can use. The laws are here. We're going to use a negation law. Let's look at the negation law. For now, let's discuss the negation law. The negation law says this. It says that the negation of P, actually here, since we're using X and Y, right? Let's say the negation says the negation of X and X. It's like you're having a statement and it's negation. You're computing them. This is going to be logically equivalent to this one will give us a false, which is a 0 in this case. We're going to use 0. Then the negation of X or X will be logically equivalent to true. Reason being, if this is 0, this one is going to be 1 because the negation of 0 is 1. And 0 times 1 will give us a 0. And if this is 1, the negation of 1 is 0, still the answer will give us a 0. So it means that for us to prove this, we're going to take the left-hand side, which is this, and we know according to that, this is the same thing as this, according to negation law. You see, right? And this will be, if we apply De Morgan's law, this one of having a negation outside and you apply it inside the brackets, it's called De Morgan's law. You see, right? And then we apply this will change to O, negation of X. And then this one will be X, the negation will cancel out. And this, we know it's this one, it's equals to 1. So the answer will be 1. So we have proven that indeed this is 1. So this is not the only question they can ask you. They can also ask you to prove that the negation of 1 is 0. So how do we prove that? Let's check. How do we show that the negation of 1 is equal to 0? So it means that we're just going to take the left-hand side. And we know that 1 is the same thing as the negation of X or X. So if it's 1, you use or. If it's 0, use and, right? Now this will be negation X. You don't apply this the same time, right? You must keep the negation, then you'll apply it later. Apply one law at a time. Then this will be X and negation of X. And we know that when it's and, we know that this will be 0. You see, right? Ne? So that's how we prove this. Boolean algebra is not that difficult. It is simple for us to work with. Now, let me see what the next question they're saying here. Let me see what they're saying on the next question. They say we must prove. Where's the next question? Okay, let me just mark it so that I know when I go back to it, it's like this. Yeah, I did mark it here. So yeah, let me just copy the question. They say now we must show. They say we must show this, and that the negation of X or Y is equal to the negation of X, and the negation of y. This is coming from a tutorial, right? Tutorial 3.5.3. So for us to prove this, guys, this is a De Morgan's law. This is De Morgan's law. This is De Morgan's law. You say, right? For us to prove this, it is sufficient. We're going to say it is sufficient, or it suffices that we can say that it suffices that it is good for us to take this and this. We prove that, remember, when it's end, if it's end, we prove that it's equals to 0. Then if it's or, we prove that it is equals to 1. You see, right now? So we're just going to say it is sufficient. Always, if you are told to prove a law, this is just a law. You see, right now? So you're going to say it is sufficient to prove that I take this inside and this one. You don't take this negation outside the brackets. You're just going to prove it is sufficient for us to prove that x and it's or y and negation of x and negation of y is equals to 0. And I take the same thing. It's like I take the same thing, now I put or in between. Now it's going to be equals to 1. I just put or here, which is equals to 1. If it's or, it should be equals to 1. So let's start with this one. So here's the thing, right? When you're proving any of these, let's say we're proving this one. If we're proving this one, right? If we want to prove that this is equals to 0, let me do this. If I want to simplify this, let's say apply distributive law, I want to distribute. You should always make sure you distribute the side that when you are distributing, the signs here are going to be the same. So there are two ways you can simplify this. You can distribute in this direction. You can also distribute in this direction. You see, the correct direction is the one where the signs are the same here. So it's this one. This is the correct one. So it means that we are going to distribute here and say that this is equal to x and negation of x and the negation of y. Then I close here, I put all. Then I distribute the one of y. I say y and negation of x and negation of y. The reason why we want the signs to be the same inside here when we're distributing is so that we can apply associative law. You say associative law or commutative law, it depends. But this one here we're applying associative, we shift brackets. So we want to apply these two laws. Here we applied associative. On the other one, this one here will be forced to shift the statements, which is commutative law. You see, right? And then this is 0. We know that. We've used it to prove before. And this is 0. 0 and 0 will still give us a 0. This one will also give us a 0. And this will be a 0. I'm sure you see this. Any question here? If you have no question, it means that now we can prove this one. Now we prove when it's or. Let's just pick the left hand side. We check if we're going to get 1. Let's see which side is the correct one to distribute. If we distribute in this side, the signs won't be the same. So it's not the correct way to distribute, meaning that we should distribute in this way. The signs are going to be the same. Meaning when I distribute here, I'm just going to say X or Y, then I distribute the negation of X, which is coming from here. Then I say and I still keep the X or Y or negation of Y. Then we proceed. Then here we apply commutative X or negation of X or Y. Then here we apply associative X or Y or negation of Y. Then here we're going to get, this is 1. No, it's all here. Or Y, X, or this is also 1. Then 1 or anything will always give us 1. That one is domination law. You see, right? Then X or 1 will always give us 1. Still domination law. Then this is idempotent of doing the same thing, computing the same element. So we get a 1. So now we have proven that these two are indeed correct. They are all indeed like that. So if you have proven this, it means that this statement is correct. You see, right? Then you say, thus the negation of X or Y is equal to the negation of X and the negation of Y. So we have proven that. You see, right? So with Boolean algebra, it's simple. You can just easily prove it anyhow. So now let's check. So it means that now we can proceed to check. Let me see. How did I skip from here to here? But yeah. So it means that now we can proceed to check. I think the next question that we have here, they say, but if I look at these questions, they are the same. They are the same. You're just gonna prove them. You just check how to prove them, right? So I've shown you already how to prove such a question. So let's go to the functions. There's also a question here based on functions. So when we come to functions, guys, we have this. When we come to functions, we're going to be looking at two types of functions, 1-to-1, and also we'll look at the onto function. This one, 1-to-1, is called injective. We're injecting. Then this one of onto, it's called surjective. Here it's an aspect that covers. We're trying to cover. I want to see if our image is going to cover the entire code domain. You see, right? So now, if both are satisfied, this is called a bijective. You see, right? Now let's check. Now we come and say this. Let's look at the question here where they say, we're in the tutorial 3.6.1. They say f from R to R defined by f of x equals to minus 3x plus 2. And the question, they say we must check whether the following functions are onto or 1-to-1. Then they say show your steps clearly, right? Now we do this. We want to check these steps clearly. First thing, let's check 1-to-1. It's much simpler to check 1-to-1. Or injective. So, if we're going to check this one, what does 1-to-1 mean? For 1-to-1, we are going to, the 1-to-1 says this, says that it says if f of x is equals to f of y, then x is equals to y. So we are going to assume this. So meaning that we should assume that f of x is equals to f of y, which this will imply that our f of x is minus 3x plus 2, which our f of y would be minus 3y plus 2. Then when we take 2 to the other side, we're going to be left with 3x equals to minus 3y. Then if we divide both sides by minus 3, we're going to be left with x equals to y. So we have indeed proven that this is 1-to-1. Say hence f is 1-to-1. Now we prove onto. I want to check if this function is onto, which is surjective. Now, for us to prove a function to be onto, we are going to first let y be an element of R, be the codomain. Because our codomain is R here, right? This is our codomain, which is R. Going to let this be the codomain R. Then we let, or let me say, instead of letting, maybe we can say such that, yeah, but it's fine. We can just let, which is also fine by letting. So let me just say, but it would be best if we just let y be equals to f of x, such that y is equals to minus 3x plus 2. I think it was 2, right? Yeah, minus 3 plus 2. Then we solve for x. The aim is to solve for x. Then we imply that if I take minus 3 to the other side, I'm just going to get 3x, which is equals to, take y to the other side, I'm going to get minus y plus 2. You see, right? Then I divide both sides by 3. Then let's check. If this is a real number, if y is a real number, whenever we plug a real number here, will we also find this thing to be a real number? That is our question. You see, right now? So, and indeed, this will be a real number for any r, not r, for any y, for any y. You see, right now? This will indeed be a real number. It won't change. It will always be a real number. Whatever number of y we plug, our x will always be a real number. So this is correct. Why am I saying it always be a real number? Because our domain is a real number. So it's, in other words, we pick y from here, then we solve for x and ask ourselves if x is covered in this domain. You say, right? So this is what we're doing for the onto. Now, if we look at the second question, okay, let me look at number 3. So here we're given f from r plus to r plus, right? They say defined by f of x is equal to x squared. You see, right? Now, we are asking ourselves, is this going to be a one-to-one? Is it going to be onto or not? You see, right? So that is the questions that we're asking ourselves. So let's first look at one-to-one. We should know that this one is injective. So we know that when we look at injective first, we are going to first assume that f of x is equal to f of y. And we know that this implies that this is going to be, if we check this, again, we were given x squared, right? So we're given that f of x is equal to x squared. So the question is how we're going to prove it. So let's check. We're going to say that x squared is equal to y squared. But these only include positive numbers. You see, this will be x is equal to y for xy element of positive real number. So we're going to specify that. This is only true if we are only considering one side. But if it was the entire real number, this was not going to be true. It was not going to hold because there will be two different numbers. So this should be unique. It should be one input for one output. You see, right? So this means, we can say hence f is one-to-one. You see, right? Now we check onto. Check surjective. Now, remember with surjective what we're going to do, right? For surjective, we're going to say, now I'm going to let y be an element of r plus, be the codomain. We're going to let this be the codomain, r plus, such that, I say that we can even say this, such that y is equal to f of x, and then we're going to have y which is equal to x squared. You see, right? Already we know that we have taken y from the positive numbers. And since y is positive, for us to solve for x, it will be simple. We're just going, because here we're only going to consider one side, right? We're only going to consider the positive part. You see, right? We won't consider plus or minus. We're only going to consider one side, right? So, because also for x, we consider one side. We say this will be an element of r plus. In other words, we're saying that we're considering one x for any y, as long as that y is in the positive part. You see, so this is going to hold. We're going to say hence f is onto. So you must keep this in mind, right? Must always keep this in mind. Now let's look at this other one. We have the last question there, which is saying f such that r maps to minus 1, 1, defined by f of x is equal to cos of x. Right? So now we check this. If we check this question, we're given this. We're given that f is moving from r to -1, 1, the closed interval of that, right? Now we're going to say now, for us to prove this, we're going to start with 1 to 1. Which is injective. We're going to check 1 to 1. We're going to assume f of x is equal to f of y, which this implies that cos of x is equal to cos of y. And this, we know that if cos of x is equal to cos of y, here does not imply that x is equal to y. This is not always true. You see, right? Then we're just going to come and say, but x is not equal to y. We can even use some counterexample. If we check, for counterexample, if we check cos, let's say, not just check cos. Let's say if we can say this, if we let x be equals to 1, not 1, let's say 0. Want something that I can easily get the solution to. X be equals to 0 and y be equals to, let's say 2 pi. You see, right? And then cos of 0 will be equals to 1. Also, cos of 2 pi will be equals to 1. Do you see this? I'm sure we can check what is cos of 2 pi. You can try to check from your side there. What is equals to... We can check what is cos of 2 pi, right? These two are equal. Cos of 0 is equal to cos of 2 pi. But 0 is not equal to 2 pi. You see, right? So 1 to 1 for this does not hold. I'm sure we said this. 1 to 1 for this does not hold. So now if if this is fine, okay, but it's fine. So let's say this, yeah, guys, I have something that I have to attend, right? Let me end here. You can just send those questions. You'll tell me what time you guys are writing. I think maybe you might be writing around 9. You'll tell me. Send me those questions. I have something to attend now. Fast. I'll come back to you guys.